and we're going to go to this other part of the experimental design possibilities, and this one is called blocking. Um, it talks about this idea that we may have within our subjects or experimental units some commonalities, and those commonalities may have attributes which are known to affect how the treatment is interpreted. So it says a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatment. Now, if we know ahead of time that they're going to interpret the treatment differently, the one thing that we want to avoid is to have all of those experimental units that react differently all in the same treatment group. Because then are we measuring how well the treatment affects the groups, or are we measuring the just the inherent difference in the two groups? So what we do to take that into account is that we do what's called a randomized block design, where we have the treatments um, assigned to um, the different treatments assigned within each block. So imagine, for example, we're taking a look at two different keyboard designs for a smartphone. And maybe this is really early in the smartphone era, and not everyone has a smartphone yet. You get 10 volunteers. Well, some of them have smartphones and some of them don't. Well, maybe the people with the smartphones have gotten used to their current keyboard layout and would be not happy about a new layout. And the non-smartphone users, oh, they don't know any different. Well, we think that the new keyboards how they're interpreted may be different within these two blocks. So this step here is called blocking. Okay. And within the smartphone users, now we can do random assignment to our two different treatment groups. Now, within this block, we can do random assignment to the two different treatment groups, and then we can then compare the results. All right. So form blocks based on the most unavoidable sources of variability, lurking variables, and then use randomization to average out all the other lurking variables that may exist. So when we know there's a problem, block on it, and then all the problems that we don't know about, we're just going to hope that the random assignment evens those out. Let's take a look at uh, a place where a block design may make a lot of sense. It says women and men respond differently to advertising. Researchers would like to design an experiment to compare the effectiveness of three different advertisements for the same product. Probably should be product. Explain why the randomized block design might be preferable to completely randomized design for this experiment. Um, we could say, well, because men and women respond differently to advertisements. We want to avoid having all women in the same treatment group, or all men in the same treatment group. right? And then our solution, blocking will keep this from happening. And because the treatment groups can't be as um, won't be as different. We'll actually get a little extra benefit. There'll be less variability in our samples. So it's outline a randomized block experiment using 300 volunteers, 180 men, and 120 women as subjects. Describe how you would carry out the random assignment for your design. All right. So let's start with, we have our subjects. And how many of them? There are 300 of them. Now let's block. I think I'm gonna need a little bit more space than that. There we go. All right. Oh, lost to this. Let's block for our men, where there's 180 of them, and then our women, where there's 120 of them. All right. And again, this step is called blocking. All right. Now, what do we do? We're going to take the men and break them into three separate groups. And this step is called random assignment. And how many go into group one? And that would be a third of them, which would be 60. How many go into group two? That will be 60 as well. And how many go into group three? And that would be 60 as well. And what happens to them? Well, this group sees advertising number one. This group sees advertisement number two. And this group sees advertisement number three. And then when we're done, amongst all the men, we can compare results. And then what happens amongst the women? Again, we break down into three groups using random assignment. Into group one. And that will be a third of 120. So there's going to be 40 in that group. Into group two, where there's 40 in that group. And group three, where there's 40 in that group. And then each of these sees the different advertisements. And when we're done, we can compare the results within the women. And when we're done, we can compare the results in general. Okay, that answers that part. It says, how would you carry out the random assignment for your design? Okay. Well, um, let's talk about doing the random assignment for the males. For the males, um, we have to break it into three groups. So I would probably put all names into or onto identical slips of paper. Put slips into hat. And of course, mix well. And mix well. Without looking, draw out 60 names. Those are assigned to group one without looking. Draw another 60 names. They are assigned to group two. All remaining names are in group three. Similarly, for women, um, except drawing out 40 names for each group. There we go. And that will give us three randomly assigned treatment groups that, again, amongst the women, all the other lurking variables um, should be then uh, distributed across the different groups. All right, we got one more experimental design, and that's called the matched pair design. Now, in the matched pair design, we have two things, a pair of similar experimental units. Now, the similar experimental units could be twins, because twins, especially if they're identical twins, or they're at least genetically uh, identical to each other. They're very similar. Okay. It could be a plot of land split in half. Okay. But what we're looking for is two things that are nearly identical. Okay. And then let chance determine which of the two in each pair gets which treatment. So you have a pair of twins, one of them's going to get an acne treatment and one of them's going to get a placebo. You've got you got a plot of land that you divide in half. One half of that plot of land is going to get herbicide A, and the other plot of land is going to get herbicide B. And what you end up getting is, again, two things nearly identical, and the only thing that's different between them is the treatment. Now, sometimes the pair can consist of a single unit that receives both treatments, meaning that a single person gets acne medicine for a little while, and then they get the placebo acne medicine for a while. And the only thing that then varies by chance is in which order the treatment is given. So people can be their own matched pair, right? Now, one of the things that's important about when we do a matched pair design, that um, we are going to not really care what happens with the acne medicine and the placebo. What we care about is the difference between the two. So it says, imagine there's an example where I take your pulse rate when you're standing and when you're sitting, and I want to know, hey, is there a difference? So half of you are assigned to the group in which you stand first, get your pulse taken, then you sit, get your pulse taken. The other group, you sit first, get your pulse taken, then you stand. And in this experiment, imagine this is all the standing pulse rates, and this is all the sitting pulse rates. And fundamentally, it doesn't look like there's a lot of difference there. But we actually don't care about that outcome. What we care about is that we look within each pair of the difference in the outcome. So, for example, for one person, it looks like the difference in their pulse rates from standing to sitting was 21 beats per minute. Okay. There's some people who actually had a lower standing heart rate than sitting, but you can take a look at that and then you ask the question, well, if standing and sitting didn't matter, what would you expect? Well, I would have expected the difference to be zero. But clearly, the vast majority of the data points, the difference is bigger than zero. So when we look at matched paired experiments, it's important that we look at the difference in the outcomes in the individual pairs, not the overall uh, uh, results from the separation. All right, so that concludes our 4.2 lecture. We learned about uh, observational studies and experiments. We learned about how to deal with multiple treatments, groups of experimental units. We learned about how to try to control by having multiple treatments. We talked about random assignment of into treatment groups, replication, about making sure that you have lots and lots of experimental units so you can actually see the difference that's really there. That behavioral issues may lead us to want to have double blind, where the subject and those they interact with don't know which of the two treatments are given. We want to make sure that we sometimes have placebos, a fake treatment to keep from dealing with the placebo effect. We also learned on how to block to control for known variations within our experimental units. And we also learned that an experimental design includes matched pairs where you take um, two things that are nearly identical, one of them getting one treatment, one getting the other, and that has its own special ramifications. And that concludes 4.2.